Well, we can increase the B field if we have more current. And if the current is in a direction where the B field from that current can reinforce itself. So here, for example, one option is to have maybe a wire loop where the current is flowing in this direction. And if we use the right-hand rule, so if I point my thumb in the direction of the current, my fingers will curl around in the direction of the B field. So in this part, we have a B field coming out of the loop. And on this side, where the current is going down, the B field goes in this direction. So it's in the middle here, you can see all the B fields from all these different parts of the loop are parallel. They want to align themselves together. And so we'll get a stronger B field in the middle of this loop than we would for a straight wire, which only has one section of current. And this is a nicer picture of what it would look like. So the B field in the center is stronger. And a question though is, can we increase it even more? Well, we're not really limited to just having one loop. Maybe we can have a whole bunch of loops all stacked on top of each other. And you might have seen this before. This is called an inductor. And it's used to store magnetic fields. So there's these purple lines here are the B fields. It can vary in time. And we can use it to store magnetic field energy. And so let's develop a voltage current relationship for this inductor, because then we can start to use it in our circuits if we have that relationship. And so let's consider an inductor. It's a wire coil like the one you see here. There's capital N number of turns. There's a current, I of T. It might vary in time. The length of the coil is L meters. There's a cross-sectional area, S. That's that shaded blue region. And let's say the area there is A, the total area. S is the surface of that area. And we're going to assume that the current is increasing in time. And so the B field, as a result, going through that coil is also going to be increasing in time. We're going to assume it's pointing in the downward direction. That happens to be this n hat direction. We don't have to get too distracted by all the details here. Just follow along in general and it'll be fine. So the B field will be increasing. And last time we also discussed Maxwell's equations. These are used to solve electromagnetic fields. EM forces turn out to be one of the 4 fundamental forces of nature. And that's why it's so important. And that's why also these come up in all sorts of technologies. We take advantage of electromagnetic fields for wireless communications, radar, cancer detection, cancer treatments. It shows up all sorts of places. So that's why these equations are so important. And last time we used Ampere's law for the capacitor. And this time we're going to turn to Faraday's law. We're going to use that to apply it to the inductor and try to get our voltage current relationship. So let's apply Faraday's law to just one turn. We're just going to consider maybe this one right here, one turn of this coil, and after that we'll sum over all of the turns of the coil. So this means that we sum up the E field around one turn. That's equal to the voltage that's induced across one turn. I'll say one turn here. And on the other side, let's assume B is constant over S, that surface area. Throughout the coil, we're going to say on the inside of the coil, B doesn't change. And so that's going to allow us to rewrite this. Instead of an integral, we don't have to take the integral anymore because it's going to be constant over that surface. We can just turn that into multiplied by the area, and now we have the magnitude of B, because it doesn't change over that region. And the B field we find, if we were to derive the B field for a long coil. We can use the Biot-Savart law. We're not going to do that in this class. It's actually a very simple law that we could pick up very quickly, but in the interest of time, I'm just going to give it to you. That is mu naught. It's a parameter that describes how the magnetization of the material in between the coil, which right now is just air. And so that's our B field from the Biot-Savart law. So I'm just going to use it here, and we'll say, okay, the voltage that's induced from one turn is, I'll say, about equal to, because we've made some assumptions here with the B field being constant, it's equal to minus mu naught NA over L. I'm just putting all this together. And then we have, depends on the time rate of change of the current. So this was for just one turn of the coil. So if we want to now get the V total for the entire coil, we would take this and we would just multiply it times capital N. So I'll write N times this whole expression. Now there's a minus sign right here, and that minus sign is from what's called Lenz's law. And again, you don't have to be really concerned about all these details, but the end result is what's important, and the fact that it comes from Maxwell's equations. What this means is that the inductor wants to push current actually upward in the coil. The current right now is flowing downwards, and it sets up a B field in the downwards direction. But the reaction of the coil is that it wants to send current in the upward direction, which would set up a B field in the upward direction. And this is what means that we get a voltage drop across the inductor. And that's because it's kind of resisting the change that's happening. The current is increasing, and it wants to oppose that increase. So that means we can ignore this minus sign, and we'll just remember that we get a voltage drop across an inductor. So this is our equation that we just got for V induced, N total turns, V for one turn. And it turns out this first expression here, if we were to derive the inductance of a wire loop, that's what we would get. So this turns out to be VL is L, and then DI L dt. So what we did was we derived the voltage current relationship for an inductor straight from Maxwell's equations, which are the fundamental equations for electric and magnetic force fields. And we can also rearrange this. If I were to solve for the current, we would get 1 over L, and we can take the integral from minus infinity to t and integrate VL with respect to time. Or you could rearrange this and solve for time equals 0. I guess I can do that. From 0 to t, we know if we close the switch right at t, we're going to see that, then you would just change the integral from 0 to t, and you would then have to add whatever the current was right at 0. If it wasn't 0, you'd have to account for that there. So all in all, what this means is that instead of just getting a current to just flow around, and it just flows around this wire loop and then flows back out again, what we get is we get an EMF. It's called an electromotive force. You might see that written in the book and so forth. And it sets up a current and a B field in the opposite direction. It wants to oppose that increasing current. And you actually get the opposite. If you decrease the current, that means it'll want to set up a B field in the opposite direction, and it'll want to oppose that decreasing current. And this is actually kind of the fundamental reasons of why we can't ever get a perfect motor or a generator, because there's this Lenz's law. You're not ever going to get a perfect conversion. This all relates together. You're not going to get a perfect conversion of energy here between magnetic fields and electric current. There's going to be some loss associated with that.